Right? Now we move to estimating the parameters. Okay? To do this, we are going to a simpler case in which sigma square is none. Okay? Sigma square is none. Okay? So then is sigma square is no more random variable. Okay? This is not random variable any longer. Okay? And beta is the only random variable. And we assume that beta is generated from this normal distribution. And then beta 0 is mean, and variance covariance matrix is sigma square times B0. Okay? So then, of course, you choose beta 0 and B0. Okay? This is your choice. These are not random variable. And then given beta and y is randomly generated from this normal distribution. And this is your belief about the y. Okay? And also this is your theory. Okay? This is your proposal that y has been generated from this process. Okay. Okay. In the first step, beta is generated, and then in the second step, y is generated from this normal distribution. Okay. Right. So then, what does it mean by estimating beta? It means that we wanna derive the conditional distribution of beta given y, and we call this what? Posterior distribution of beta. This is what? This is prior distribution of beta. Okay, this is prior distribution of beta. What does it mean by prior? Prior means prior to observations, prior to the time you observe the data. Okay, before you observe data, you believe that beta must be around beta 0, but it's not certain. Okay, if sigma square times B0, particularly B0 is very, very small, then your belief is very strong that beta must be very close to beta 0. In contrast, if B0 is very, very large, that means you guess that beta could be around beta 0, but it's not that certain. It could be much smaller or much larger than beta 0. That's why you put very large number on B0. Okay? This is your choice based on your theory, intuition, or experience, whatever, or just the reading literatures. Okay. 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 And then also what does it mean by estimating posterior distribution or conditional distribution of beta? And intuitively, it's simply you wanna estimate conditional mean and conditional variance of beta given y. Conditional mean, you will see that conditional mean corresponds to the beta hat OLS, and conditional variance of beta is very similar to the variance of beta hat OLS, like this. Okay, so this is a sort of the mean and variance of beta given y. Okay, we are going to derive this later. Okay. Okay. Again, our job at this point, is to derive the conditional distribution of beta, and then to figure out what kind of distribution is. We wanna try to compute its density function, and then it happens to be that the density function is known, and or the density function is a standard. Then we can immediately see that the beta follows normal distribution, t distribution, whatever. Okay. Okay. So then we are going to compute the conditional density of beta, or we said posterior density of beta. Okay, using this Bayes rule. Okay, Bayes rule. Then again, we as we learned from the flipping coins, then to figure out the kind of the distribution of the parameters, we just compute its kernel, not full functional form of the full functional form of the density function, right? So then again here, this is the likelihood, and this is prior density, and this is, we say, marginal density. Just don't care at this point. The point is that y is random or non-random at this point. At this point, y is not random. This is fixed. Y is observations. Y are just fixed numbers in Excel file. Okay, y is just fixed data. Okay, observed from the website or the literatures. Okay, so y any y is fixed. You cannot change y. Okay, y is given. Y is no more random variable, and so that means y is just number, and f of y must be a number. Of course, we don't know what exactly this number is. The point anyway, the point is that f of y is just number. That means this doesn't change. This doesn't change according to beta. Okay, this is not a function of beta, and this is a function of beta, and this is a function of beta. So this posterior density is proportional to the product of the likelihood and prior, right here. Okay, so we don't care about this constant because we want to just figure out the kernel or the just essence of the density function, which is subject to the beta. Okay, again, we know that y follows normal distribution given beta. Without beta, we don't know what kind of distribution is, but we know that once beta is given here, once beta is given, then y follows normal distribution. If beta is not given, we don't know, right? We don't know. We have no idea what kind of distribution is, but we are sure that beta y follows normal distribution given beta. So that's why here this is normal density. So density of y given mean is x times beta, and the variance covariance is sigma squared times identity matrix. Okay, this is normal density. And also we assume that beta follows a normal density, and its mean is beta 0, and variance covariance is sigma squared times b0, right? So then by the definition of multivariate normal density, so this is likelihood, and then y is kept t by 1. This is multivariate now, right? Not univariate. And this is definition of multivariate normal density. And its mean is x beta. The variance is sigma squared times identity matrix. And actually, this here must be inverse of identity matrix, but it's still identity matrix. So that's why there's no identity matrix here. Okay, and this is the prior density of beta. Of course, beta follows normal distribution, and this is also the this is from the definition of the multivariate normal density here, and so mean is beta 0, and variance covariance is sigma squared times b0. Okay, so this absolutely means the determinants of the matrix, right? Okay, and so then this posterior density is proportional to the likelihood times prior, and this is the likelihood, and this is the prior, and you see that this likelihood is a function of what? Function of y or beta. Y or beta. This is a function of beta. Why? Because y is fixed. Okay, y is fixed on the y is a fixed number. Okay, these observations. Okay, fixed and contained in an Excel file. Okay, and then beta is unknown, right? So if you put different beta different values of beta, then you will get different values of the likelihood. right? Okay, and of course this pi is a function of beta, of course. Okay, and then here again, our interest is the Cornell. Okay, so that means these are just constant. Okay, these are just constant. These are just normalizing constant, right? Right. So then here, okay. So then we can write this. This posterior density is proportional this exponent times and this another exponent, right? And then here is exponent times exponent. Then here this term, this exponent, exponential function of this exponent plus this exponent, right? And that's why we have this, right? This, right? And then we are going to arrange this equation in terms of what? In terms of beta, to see what kind of density it is. Okay. So then, right? There's one more. I think there must be one more equation to explain more friendly. Okay, so then let me change the source file. Okay, all right. Okay, let's do this. Okay. So this is the source file. Okay. We call this LaTeX. This is a sort of the academic. This is a academic word processor. Right here. Okay. Let me put another equation here, and here this is prime. Okay, this is not derivative. The prime, and prime here. Then it must be y prime times here. Then x beta primes. X beta primes means that, okay, let me here. Now here, x beta primes, right? And this beta prime, beta prime and beta 0 prime. Okay. And then here, okay, let me put this. Here, y prime minus x beta prime must be beta prime times x prime. We should change the order, okay? And y minus x beta. Okay, let me put here as x, okay, x beta prime should be, this is equal to beta prime s prime, not x prime times beta prime. Okay. So then, yeah. Then we can move to the next line. Yeah, I think so. Yeah. All right. Okay, let me save it. And then I should compile it. Okay. I can compile this to the PDF, but this interface is quite unstable, so I need to open another the editor here. So actually the word process is also the coding. Okay. Oh, I should close this file first. All right. Once again. So the reason why I use this LaTeX is that the fonts, I mean, particularly the mathematical fonts for the mathematical expressions are so beautiful. Okay, much better than the Microsoft Word and the Hangul. Okay, it looks much more professional. Yeah. See, these equations are very beautiful and pretty. Yeah, can't be better. Yeah. Okay, right. Okay. Again, here. So then this equation is now here, right? We just derive this. And then here y prime, y prime minus y prime x beta, beta prime x prime times y, right? So we will have 4 terms. And then also here, the beta prime times b0 inverse minus beta 0, so beta 0 prime times b0 inverse times here beta minus beta 0. We're gonna do this. This is just algebra, okay? It's very simple algebra, okay? Then finally we have this. Okay? And at this point, you see, sorry, I think we need one more line. Then, okay, here, just let me give you, let me explain by words here. Here, y prime times minus x beta, right? Y prime times x beta here, and then here another term, beta prime times x prime times y, right? So, and then you will see that this y prime times x beta equals beta prime times x prime times y. These two terms are equal, and let me explain why. Okay, here beta prime, beta, the dimension of the beta is what? Beta is k by 1, and k by 1 here is prime. This transpose, it means that it must be what? 1 by k, right? This is 1 by k. What about x? X is what? X is t by k, but here is prime. That means it's k by t. And what about y? Y is what? T by 1, right? So then these two numbers are the same, these two numbers are the same, right? That's why we can compute these multiplications. Otherwise it's not possible, right? This, because these two numbers are the same, that's why we can do the multiplication between these matrices, right? So then, and then what of the output? What's the dimension of the output? Dimension of the output is the first one, the last one, 1 by 1, 1 by 1. So this is 1 by 1. Each vectors or matrices are not scalar, okay? But their multiplication is now just scalar, 1 by 1. And also, what about this? What about this? This is what? Y is cap t by 1, but here is prime, 1 by cap t. Here x is t by k. Beta is what? K by 1, right? So then the output is 1 by 1. Output is 1 by 1, right? So then, so this is scalar. The point is that this scalar and this is a scalar, right? And then if I put, okay, let me erase it. Okay. here. And then here, if I put transpose here, transpose, and if you do this, it's what? We have to reverse the order, right? Beta prime x prime y transpose must be what? Y transpose y prime, and x transpose and transpose, which means just simply x. What about beta transpose transpose? Then means that's beta, right? Which is equal to this. So, right? You can see now. What about the transpose of scalar? Transpose of scalar must be itself, right? And then you see that transpose of this equals to this, and both of them are scalar. So then that's why these two values must be the same. And similarly, you will see that here, beta 0 B0 inverse times beta, and beta 0 prime B0 inverse. I'm sorry, beta prime B0 inverse and beta 0. And beta 0 prime B0 inverse and beta must be the same. Because this is also what? This is also scalar. And this is also scalar, and transpose of this is equal to this one. That's why these two numbers must be the same, right? That's why we have 2 times beta prime x prime y. Here, 2 times beta prime B0 inverse times beta 0. Okay? Beta 0. Okay? So then here, now, and then again, this is a function of beta, right? And what about this? Y prime y. Beta 0 times B0 inverse times B0. These are not relevant for beta. Okay, these are just constant. Y is just number. What about beta 0 and B0? Beta 0 and B0 are known. These are chosen by yourself, and you know the numbers for beta 0 and B0, right? So then these are just, but these are in this exponential function, so right? So then this is just this multiplication, right? So then that's why we ignored these terms, and that's why we have just proportional, right? This is another proportional, right? So then the remaining is this term, this term, this term, and this term, right? So then this term is just this term square term. Sorry, this is quadratic term, right? Or quadratic or beta square term, because here beta prime beta, okay, and then this is the this is the linear term. There's only beta, okay, only beta, right? So then again, that's why we have the beta square, beta, and another beta square term. Oh yeah, that's right. So this is beta square term, and this is just beta term, right? So then look at here, beta prime, beta. Here, beta prime and beta, right? So then we can put these two terms together. Here, beta prime, and this is right, the beta, and then between them we can put x prime x and B0 inverse. So then now we have one unified term here, and then here's minus 2 beta prime, and this is another minus 2 times beta prime. So this is another term. This is just here is beta term, here is beta square term, right? Okay, so then at this point let's take a break.